My name is Zeng, and this is Zhong to work with my previous PhD student, Chao Dong. Right now, he's working for Amazon. So let's start. So what is inverse optimization? Actually, the story is a very old-fashioned. We as a human or enterprise or organizations, we are making decisions every day, every moment and anywhere, right? Sometimes people want to understand the reason, the mechanism or the reasoning behind, because our decisions are reflecting our interest, our desire, our preference, or utility function in general. And sometimes we are subject to different restrictions, like a budget or resources. So on one side, the decisions, like in the format of choice, behavior, operations, they are observable. They can be observed and stored as data. But for service provider or manufacturer, even from supplier, we would like to understand our customers. We would like to understand our clients. So if we can understand them a little bit better, we can provide better quality. Some chat. And so right now, let's talk about how to recover data, recover decision-making problem from the observations, from our observed data. Okay, one example actually happening in our real life is it happens everywhere in the world. We notice someone using umbrella outside, but we know one knowledge: using umbrella can cover ourselves from rain. So one inference is it's raining right now, and people we don't like wear the wet clothes. Right? This is the inference. Actually, the inference involves some decision making in our mind, but this is a very simple situation. In other situations, the problem can be more complicated. In any case, we would like to develop a methodology to do that job. So there are some assumptions. We believe the decision makers are rational. So that means they acquire and carry out optimal decisions in their decision-making problem. And the decision makers, sometimes they are doing single objective function, like we try to minimize the distance, or we just try to minimize the traveling time. And some other times, it's a trade-off between multiple object functions, like a risk and returns in finance, right? It happens a lot. So, as I mentioned, the whole motivation is, can we recover the decision-making problem from observations, either utility function or restrictions, or the overall decision-making scheme? So that's the idea, that's a motivation, that's a driving force of the inverse rotation. Based on data, how to infer or how to understand the decision makers' decision-making scheme or mechanism. The first part I'm gonna go through today is inverse rotation with online learning. But this part actually is a little bit it's easier to access, and the background is kind of like easy to understand. So the things come the background like this, the layout like this. We have a set of observations. They are probably noisy or suboptimal, and we want to infer the decision-making parameters with a single object function. So this assumption actually indicate we try to understand a single decision maker and a single object function. Because if you have multiple decision makers, they may make differences in different ways. If they are making these differences, if they are making decisions in different ways, probably cannot use a single decision-making problem to reflect their reasoning procedures. Here we will talk about single decision maker and the single object function. One situation is like the utility maximization problem. We have N products in the market, and we have budget B. We want to maximize the utility function over those products, but prices are changing over time. Let me start. So the price change over a different time. Price change from month to month. So we interpret price as an external signal and the X is our decision. Okay. I want to highlight we have an external signal and we have a decision. Okay, so we have signal and the decision a pair. In the traditional inverse optimization theory, we want to typically people deal with a set of observations and do the job in a batch way. But right now, the batch way is hard to support the AI enabled applications. Like in this case, the recommendation system made by the movie theater, the online streaming video providers, they actually collect data based on your history, and then they make a recommendation to you. But that your purchasing decision is occurred over time, time by time. It's not available at the same time. So the traditional inverse optimization, they are powerful in analyzing standard optimization problem, but they have a hard time to deal with sequentially arrived data. And overall, the problem actually is NP hard. So instead of assuming data available at the same time, we can do another approach. We deal with data in on the fly, in an online approach. So in this study, we formulate an inverse optimization problem, consider noisy data, and try to develop some online learning algorithm so that we can derive the unknown parameters in both object functions and constraints. The key feature in our algorithm is we should be able to incorporate the sequentially arrived observations in a fast way without keeping data in the memory. Okay. So it can be treated as an incremental learning. We're going to revise and reuse our previous existing inference. But for online learning, the evaluation criteria probably is a little bit different from the batch size based learning or inference problem. Before that, let's lay out the mathematical part. So in this page, we give the abstract format of the decision making problem. So we have object function, we have constraints, and we have feasible region. But feasible region actually is a parameterized by theta. Theta is a parameter we're going to learn, we're going to infer from the observed decisions. And key concept here is, as we mentioned, we have assumed the decision makers are rational. So that means the decisions we observed or we monitored actually reflect their optimal decision or optimal desire. They are not choosing decision randomly. Their decision reflects some desires. They have a reflect their strategy to maximize or minimize. So to describe the optimization part, we can introduce the optimal solution set. So the observation we have seen from practice should be a component in the optimal solution set. So here we are using SU theta to represent the optimal solution set. As I mentioned, U is the external signal, and theta actually is a parameter of the decision-making problem. Okay. And some standard assumption is we assume the space for the theta is a convex, and also it's within a radius d, and those parameters are kind of useful for us to prove the convergence of the algorithm. Okay, but that part we don't need to go to detail. You guys can check the paper, which appears in NeurIPS and ICML. So as I mentioned, in the conventional way, is people try to minimize some error, some loss function with a whole set of observations. As I mentioned, it's called batch-based inverse optimization. You can tell from the object function is to minimize the average loss function. So here L, yi, ui, theta is a loss function, depend on your definition. But overall, it's describes the discrepancy between the inferred result and the observation. Okay, so this is a batch size, batch way. In online approach, we're gonna receive the signal noise decision pair one by one. Since we receive the data one by one, we're gonna make a set of inference. So the inference can be organized into a sequence. Let's say we have T rounds inference opportunities. We're gonna have theta 1 up to theta T. Those are our inferred parameters. And as I mentioned, because we are dealing with online approach, so our ops function is kind of different from the batch norm, a batch-sized inverse optimization. So one way to evaluate the algorithm is to evaluate the regret. But what is regret? Regret is if you have the accumulated difference, accumulated loss function against the possible loss when you have all the informations, all the observations at the same time. So here I give the definition of the regret. The first term is the accumulated loss over the T rounds, and the second term actually is assuming you have all the information, and you do the minimization over the loss function. You can have your then you have a value. So the difference between them indicates how good is your online learning algorithm. Okay. If RT goes to smaller and smaller, I mean, definitely won't be smaller. If RT is the increase of RT is smaller than the number of iterations, then that indicates your online learning algorithm actually is pretty good. But if this one goes like it's much slower than the number of iterations, number of rounds, then that online learning algorithm actually is pretty powerful. So about what is our loss function here? Our loss function actually is here. This is the standard way, just to the L2 norm between the observation and the inferred decision. But here I highlight X. X need to belong to the optimal solution set, right? In the optimization problem, if the problem is linear, we can have either KKT condition or strong duality. If it's a general convex, we can have KKT conditions to describe the optimal solution set, right? So this is a common knowledge for every OR student, I guess. So here, our idea is once we have the T signal and the noisy decision pair, let's say they are UT and YT, we update our inference by using this formulation. Actually, it's to solve a small size optimization problem to do the updating. Theta T is our previous inference, and eta T is our learning rate. So we are trying to balance between our previous inference estimation and our current in the T+1 round loss function. So this equation reflects our two things. We try to balance between conservativeness, which is the first term, try to minimize the difference between the current inference and the previous one. And also the second term is correctiveness, try to update the inference as much as we can using the new information. So eta T is a parameter controlled by you. And there's no closed form, as I said, we have to solve this small size optimization problem. So since there's no closed form, we call this equation an implicit updating rule. So the whole algorithm actually is kind of straightforward. We go from 1 to T. Let's say we have T round, T's pair of information available. Once we receive the external signal and observation, we compute the loss function. As if you recall, loss function is a L2 norm between the observation and the inferred decision. If the loss function equals 0, we use the previous inference. Otherwise, we compute the implicit updating rule, and we update our inference like this. So the algorithm actually is pretty straightforward. It's a balance between all the inference and the impact of the current observation. But we want to analyze how good the algorithm could be. So we try to provide a bound on regret. If you recall, regret RT measure the cumulative loss from sequential online learning algorithm with respect to the batch norm, batch optimization inverse optimization. So we can prove the RT, the regret actually is bounded above by the square root of T. T is the number of iterations, number of rounds. So it's actually pretty nice because overall it's increased much slower with respect to the number of rounds. If we consider the average regret, the average actually goes to 0, right? Because it's a square root of T. So as a corollary, we can prove the average in long-term loss function will approach to the expected loss function if we let the number of rounds goes to infinite. Any questions so far? So let's see. I mean, this is like a nice property to understand our algorithm. But right now let's run some experiment to test how great it is. So right now let's consider a utility maximization function, maximization problem. As I mentioned, PT is a pricing information. It's change over T. Okay, and we want to understand the a quadratic utility function. Here Q is a symmetric negative semi-definite matrices, and R is a linear function. I mean, a affine function. So in our experiment, actually, we try to infer R and the right-hand side B, the budget. So let's check the inference on the R part. So we can see the X horizontal coordinate represents the number of rounds, and the Y axis represents the discrepancy. You can see the discrepancy in R part. You can see that with the number of rounds goes larger and larger, the arrow almost disappear. Also for the loss part also decrease a lot. And dot actually is a loss per round, but if you take average, the average cumulative loss goes to smaller and smaller. Okay, very small. And for finally it converge with the batch optimization inverse optimization problem. And this is a learning of the budget. Learning of the budget actually is easier. You can see the difference decreases dramatically faster. Okay, because budget is just a single number, but the R part, the return part, which the linear coefficient are a set of coefficients, not a single scalar. Another application we did is we try to learn the translation cost on each arc. Okay, this problem happens in translation industry a lot. In the real life, we have observation on the traffic on the road, and so that means we observe the behavior of the drivers. But we may want to infer the cost of each arc for people if we treat people as a single decision maker. So we have observations from the road conditions, and we try to estimate the cost of the translation cost of the road segment for every segment. So here is a twice size example. Again, we are using our algorithm. We can see the with number round goes larger and larger. The difference is much smaller. Okay, similar observation we have made for the utility maximization problem. So that's these two set of experiments support the advantage of our learning algorithm and the efficiency of the algorithm, because we can deal with online data, we can deal with the sequentially arrived data easily, much easier than using the batch inverse optimization. Any question before I start a little bit harder one? No? Okay. Probably we can resolve the question at the end of the seminar. So the second part I'm gonna present is actually our major work is the inverse multi-objective optimization problem. The motivation is kind of different because the first part of inverse optimization is well defined. It's in the literature for many years. But for multi-function optimization, it's kind of more interesting, and it's its applicability is much wider. Okay. The reason is decision, actually, we make decision not in a static way. We make decision in a dynamic way. From time to time, we may have different preference over multiple criteria. It happens a lot, right? Even in summer and in winter, we have different preference on a set of evaluation criteria. So, and also some different people, different decision makers, they share the similar evaluation criteria. Like you and me, we have some common grounds. We say something good, we say something bad, but we may have a different preference. We may have different priorities on those evaluation criteria. So if we are using inverse, if we are using multi-objective optimization, it's going to give us a great flexibility to deal with observation, to deal with data. It can help us to infer the common ground. I mean, the common ground here means the multiple evaluation criteria shared by the whole decision makers, and also may help us to understand how people different from each other. So that means how many people are risk seeking, how many people are risk aversion, right? People are different. And when we design product or provide service, we can design our service, or we can manufacture our product according to the distribution of the preference over those evaluation criteria. So overall, this multi-objective optimization problem actually give us a powerful tool to understand a population of decision maker. We don't need to assume they are the single. Excuse me. They are homogeneous. We don't need to assume that. We can understand a population of decision maker. That give us a broader scope to apply our methodology. So in our case, the inverse multi-objective optimization is we try to collect data from many different decision makers, and then we do the inverse operation to understand the parameter. I'm sorry, that's a typo. To understand the parameter of the theta of the multi-objective decision-making problem. As I mentioned, one typical application in finance, right? This is here I give the mathematical formulation, the classical Markowitz mean variance optimization problem. So at one time we want to maximize return. Here is a minimize minus return, and at the same time we want to minimize risk. We use this formulation in finance industry a lot to determine the investment portfolio. So this reflects two object functions. When we talk about multi-objective optimization, one key concept we have to introduce is the Pareto optimal, because we have a vector of the evaluation criteria. We cannot easily say one solution is better than the other one. We have to use the Pareto optimal concept to do the evaluation. Pareto optimal, so I guess for almost everybody here understand what is Pareto. I just give a quick review. This green line represents the Pareto frontier. That's in the object function value space. So anything, because bear in mind this is a minimization problem. Anything above this curve is not optimal, because we can always find solution, find the point dominate the solution above this curve, the green curve. So on the right figure shows the Pareto optimal solution set. This is a figure in the solution space. One key thing I want to highlight is very different from convex optimization. Even the problem is convex. The Pareto optimal solution set is non-convex. You can see the red curve. Okay, the red curve actually is the Pareto optimal solution set. It's non-convex because it's just a curve. But in the traditional single object function optimization problem, if you are dealing with convex problem, the optimal solution set is always convex. That can be easily proven. So that gives us a lot of advantage. But for the multi-objective optimization problem, even the underlying object functions and the constraints are convex, we cannot conclude the Pareto optimal solution is convex. So it's really hard. It's non-convex optimization problem. One common way to address the multiple object function is to use the weighted summation, right? Here we give the weighted summation problem. So we just give the object function different weights and do the summation them together. So we can have a single object function. If we varying the weights, we can have a we can derive the whole Pareto optimal solution set, okay, and some mild condition. Okay. Weights can be drawn from a p-1 simplex. P represents number of object functions. So if you draw the weights from this set, the p-1 simplex set, summation equal to 1, we can guarantee we can rebuild the Pareto optimal solution set if we enumerate every W, every weight in this p-1 simplex. But there's an infinite number of weights available in this simplex, right? So maybe we cannot enumerate. Some idea is, can we like do sampling? Okay. But before that, let me address why we want to deal with why do we want to deal with inverse optimization, inverse multi-object function optimization instead of assuming a single object function? You may wonder, assuming a single object function is like a feasible and simple and fast approach to do that. The result is it's simple, it's fast, but the result is inaccurate. Sometimes could be troublemaking. So let's consider this case. It's a two object functions linear optimization problem. Okay. The right figure shows the feasible region. Actually, for this simple two object function linear programming, the Pareto optimal solution is from O to A and O to B. But let's assume we have a lot of observations from CA and BD. So we have observations, two groups of observations. But if we treat observations as a noisy decisions, using single objective function to do the approximation, we may land it with inference of this one. If we do the D noise, we may have X star. If once we have X star, we do the inference, we're gonna have a result like this. The inferred object function will be minus X1 minus X2. But actually our object function is to minimize X1, X2, not minimize minus X1 minus X2. So you can see the inference we can have are totally different. On one hand, we just try to minimize X1, X2. On the other hand, if you are using single object function to do inference, you want to maximize X1 plus X2. So the results are very opposite, totally different. So this story tells us instead of using single object function optimization to do the approximation, we have to go back to the fundamental structure of the multi-objective function and do the inverse from that part. Okay. One challenge actually different from the single objective function inverse optimization. One big challenge is, let me show the title. The big challenge is inverse multiple objective optimization problem is unsupervised learning task. Why is it unsupervised? Because when you have even you have an observation, you know the evaluation criteria, you don't know the weight. So since you are lacking of the weight information, you don't know how to build the optimal solution set. I mean the Pareto optimal solution set. So the problem becomes it's an unsupervised learning task, and instead of supervised learning, in the case of the single objective function inverse optimization. So the problem is difficult. And let's show the idea we just mentioned. As we mentioned, if you can enumerate all the weights, you can have the Pareto optimal solution set. But that's an infinite number of weights, right? So one strategy to avoid that part is can we do sampling? So here shows the three-dimensional simplex and two-dimensional simplex is in the three-dimensional space. If we do the sampling, we have discrete points on the per optimal solution set. Because it's discrete, but we don't know which solution should match with our observation. If you don't know, by recall what we learned from integer programming, we can introduce binary variable, right? We can introduce a binary variable. Let me see. We can introduce a binary variable to find the point that with the least distance to the observation. So by doing this, we can have a surrogate loss function from sampling. So the binary variable, actually, we need to have a constraint summation of the binary variable equals 1, because we just need to pick up a single solution, single weight to match the observation. So we can define our loss function by introducing binary variable and incorporating binary variable in the object function in the object function, so that we can use binary variable to select the solution from optimal solution set of each weight samples. And when you may wonder, how many samples do we have to ensure the quality of the approximation? Here we prove a theoretical result. The difference from samples to the true difference actually is in the order of a big O of 1 over K. K is number of samples. So the quality actually is pretty good. If you increase your number of samples, the error, the discrepancy will decrease a lot. If you are talking about two object functions, but in general, it's bounded by this expression, a little bit complicated. So right now, with this new definition of the loss function, we can start building our inverse multi-objective optimization problem. So this is the whole formulation. Again, we want to minimize the average loss function, but the loss function is expanded with a set of binary variable. Binary variable is indexed by number of observations and the number of weights, number of samples in the weight space. So you can see there's a huge number of binary variables will be involved. So the problem is very difficult. It's huge, very challenging to solve. You may wonder, why should I bother to solve this huge, complicated mixed integer nonlinear programming problem? We have nonlinear object function, we have a lot of integer variables. And also the optimal solution set is non-trivial because we have to introduce the KD condition or strong duality to represent. So overall, the formulation is actually quite complicated. Once I see this formulation, I don't like either, but there are a lot of things we can analyze. We can do the simplification, and then those analysis and simplification can help us to develop fast algorithm to support the real applications. The first one I'm going to show is the linkage to the k-mean problem. But before that, let me give you some like a theoretical result. So as we mentioned here, we have observations, number of observations, we have samples k. And this formulation, before we do the simplification, how it helps us to infer the true parameters. So we did a little bit of theoretical analysis. We can prove with number of n increase, with number of k increase, the error term will go to with probability to the true error term if we have every infinite number of observations, if we have infinite number of samples. Okay, so this is more for theoretical understanding, but for practical usage, we don't need to worry at this moment. So as I mentioned, the problem is the inverse multi-objective optimization problem is the formulation is too complicated. We have nonlinear object function, we have a lot of binary variables. So we are a little bit discouraged by that formulation, but after spending some time, we found this formulation actually is close relationship with a k-mean clustering problem. Let me first give you the k-mean plus problem. So this is formulation, the k-mean. K-mean, I guess, if you're doing data mining or machine learning, everybody knows k-mean, right? So k-mean formulation is k-mean formulation is widely recognized in the machine learning AI literature. The k-mean problem is we have n observations. We need to cluster them into k clusters, such that the average square distance between each observation and the closest centroid is minimized. The mathematical formulation can be written like this. We also have a binary variable between number of observations and the number of clusters. And also it's a nonlinear, right, quadratic form. If we do the comparison between these two formulations, actually they are very close. On one hand, in the inverse optimization, we require xk belong to optimal solution set of wk. Wk is the sampled weight. On the other hand, for the k-mean clustering, xk is just a centroid, it's free. So that means if we relax this optimal solution set requirement, these two problems are actually identical. So this connection tells us maybe we can borrow some ideas from k-mean clustering to support our inverse optimization. And also this connection also indicate our problem is hard, because we know k-mean clustering is a NP hard. So our problem is definitely hard. And because our problem is k-mean is a special case of our problem. So we can prove inverse multi-objective optimization problem is NP hard. As I mentioned, we can borrow some idea from k-mean clustering to support our solution procedure of the inverse optimization. The idea we do is we manually, or before computing, we partition the observations into k clusters, and we compute the centroid of the k cluster, like here. And we just do the inverse optimization for those centroids. By doing that, we can handle millions of data, as long as we have a small number of k. Because in our computation, the only thing we have to deal with is the centroid of the cluster. So if you can control the number of cluster, you can control infinite number of data. That's give a lot of advantage. So the algorithm like this, we partition the data observation into k clusters using some k-mean algorithm, and then we compute the centroid, and then we do the k-mean inverse multiple objective function optimization problem to get the initial estimation of theta. And we design some stopping condition. If the result is good, we are done. If the result is not good, we have to go back to the cluster and redo the sum cluster. Okay, recompute the centroid until we can reach some stopping condition. Okay. So this is one idea we can do to simplify our computation. There's another idea which is more interesting, is a manifold. I guess I assume many of you have already had some background on manifold, but it's kind of new to me. So manifold is actually the internal or low dimension representation of a high dimension data, right? This is my understanding. So if you can reduce the high dimension data into a low dimension, and you can deal with a small data without losing too much information, and we can still guarantee the quality. But in our case, why manifold can play some role? The interesting part comes from our multi-objective function optimization problem. Our case, as I mentioned, we can enumerate the ways to rebuild the Pareto optimal solution set. But if we have a p functions, the weights actually can be drawn from p-1 simplex. So if you have weights, you have an optimization solution set. But regardless the dimension of the variables, we just need a p-1 dimensional piecewise continuous manifold, because the weights determine the optimal solution set. So number function is p, the manifold dimension is p-1. So we don't need to care about the dimension of the variables. We just need to focus the number of functions in the object function. Okay. This observation is a very interesting, because it enables us to apply some manifold learning algorithm to further reduce the computation burden. Here I want to show you some figure. Oh, actually, there's a special case. If functions are linear, if object functions and constraints are linear, we can guarantee the Pareto optimal solution set is a p-dimensional piecewise linear function, a piecewise linear manifold. I'll give you this figure. So here we have three functions, okay? And these the figure shows the whole parallel optimal solution set. But actually, this you can see this figure actually two-dimensional, because we have p equals 3. That means that the manifold is two-dimensional manifold. You can tell from figure there's two pieces. One piece is this linear is a plane. There's another linear plane. So actually, it's a two-dimensional manifold. Okay, but this observation helps us a lot. Back to this figure. Back to this example, we have this two-dimensional two object functions, but actually the parallel optimal solution set is one-dimensional. Okay, it's different from our understanding, but bear in mind the parallel optimal solution set is a one-dimensional manifold. I'm going to show you in some numerical study. This observation will help us a lot. With this understanding, we can modify our algorithm. Before we apply the k-mean algorithm, we can insert some nonlinear manifold learning algorithm to deal with data, to reduce the dimension of the data into a lower dimension manifold. And then we continue our k-mean based heuristic to do the inverse operation. Okay. So left figure shows the result before without using manifold learning. And the right figure shows after using the manifold learning. If we do not using the manifold learning, the red dots shows our learned inferred parallel optimal solution set. The yellow line actually is the optimal solution set. So the red dot actually is quite different from the yellow line, the parallel optimal solution set. But if you apply the manifold learning, we can see they're almost a match. So this indicates we can improve the inference quality a lot by using manifold learning before we do the k-mean clustering-based heuristic. Okay. So here we show some example using the mean variance portfolio selection problem. The figure shows that if we increase the number of samples in the weights, we can increase the quality of the inference. The blue dots represent the true efficient frontier. Okay, and because the y-axis is the mean of the return, and the x-axis is the standard deviation of the risk of the variance. So the blue dot shows the true efficient frontier. But if you have a small samples like k equals 3, this inference is very different from the true frontier. But if we increase k, the number of samples in the weight space to 21, that we have purple dots. The line of purple dots is really close to the true efficient parallel frontier. So that indicates learning. We can learn the true result pretty well. Okay, right now let me try to summarize. Today we described two research tasks. One is that we have a online learning algorithm to eliciting decision makers' preference and restrictions. Okay, this algorithm can converge pretty fast. We can learn the convex utility function and restriction easily. And because it's fast, we are expecting we can use it to address more applications. So unlike the future work focus on how to address the real applications using our online learning method. One example Chaozheng has done a little bit is designing recommender system. Another one we focus more is developing a inverse multi-object function optimization problem. We try to infer the parameter of the multiple criteria. And in this part, we provide some like solid analysis to ensure the statistical inference between our model and the true result. I mean, the noiseless result. Our focus actually is on we review a hidden connection between the inverse multi-objective optimization problem and the k-mean problem. And we make use of this connection to design some fast algorithm. And also we, together with a manifold structure, we can enhance the algorithm to deal with large data set. we have a couple online work right now. One is solve this multi-objective inverse optimization problem using online learning strategy. Another one is try to incorporate some like distributional information to help us to build more robust inverse multiple objective optimization problem. And right now, actually, Chaosheng is collaborating with Vanguard in learning time varying risk preference from investment portfolio. They have some result, and right now, actually, I believe the result is has been posted in archive. Okay, thank you. That's all my presentation today.